Hello and welcome, coming to you once again, not quite live from One Take Studios, where today's topic is solving systems by graphing. Specifically, we're going to talk about solving linear systems today, although what we talk about is actually true for all kinds of systems, and my camera insists on zooming in and out today, so hopefully it settles down soon. Alright, so here's our number one question of the day. When you have more than one equation, what's the solution? How do you find a solution if you've got multiple equations? Well, it becomes not a matter of x equals 5 or x equals 17 or whatever, but it actually is going to be a point that works in both equations. So when we talk about having systems, we're talking about having at least two equations with at least two variables that we do not know. And so in this case, x and y would be missing. X and y is a point, and if that point works in both equations at the same time, then it is going to be a solution to the system. Alright, so what would that look like just on a basis, standby basis here? Alright, so forget the graphing for a moment. Let's just check this out. Here is a system right here. I've got 2x minus y equals negative 5. Boom. And I've also got x plus 3y equals 1. That is my system of equations. I'm looking for the solution to both of them, which means I want the one point that works in both of these equations at the same time. What about 1, 7? Maybe that one works. Shouldn't I try it? See what happens? Yeah, okay, we can do that. So let's do a little bit of color coding here to make sure that we can follow this okay. Alright, so I'm going to start working with this equation first. So we're going to call this equation number 1 in blue. It's a light blue if you can tell. And we're going to work over here with this equation saying, okay, if this is 2x minus y, I'm going to go ahead and write this out. 2x minus y equals negative 5. And I'm saying, will this actually work in both of these? So let's put the 1 in for x. So this becomes 2 times 1 minus y is 7. And that's supposed to equal negative 5. Well, that's 2 times 1 is 2. Why do I have weird parentheses? I don't know. There we go. Let's do that. So this is 2 minus 7. 2 minus 7, which, you know what? 2 minus 7 actually does equal negative 5. Should we jump up and down with excitement saying, hey, this point works? Maybe. If you want to do just a tiny bit of excitement, you can. But ultimately, we are not done because this point has to work in both equations. So let's see if it works in the other one. So here's equation number 2 in red, number 2 in red. All right, and so we're going to do the same thing as before. We've got the 2x minus y equals, oops, not that one. Not the exact same thing as before. That'd be kind of silly. All right, second equation, x plus 3y equals 1. Same thing, what if x is 1 and y is 7? So that means x becomes 1 plus 3 times y is 3 times 7 equals 1. That means I have 1 plus 21 equals 1. Hey, guys, 1 plus 21 is 22. 22 most definitely does not equal 1. So is this point a solution for the system? No, it's a solution for the first equation, but not the second one. And since the system includes both of them, is this a solution? We would say absolutely no, not going to work. What about this one? Negative 2, 1. What if we try that? Again, the first one in blue. So again, we're going with the 2x minus y equals negative 5. Well, what if we put in a negative 2 for x this time and a 1 for y? That becomes 2 times negative 2 minus a 1 equals negative 5. That's going to be negative 4 minus 1 equals negative 5. Hey, negative 4 minus negative 1 is negative 5, and negative 5 equals negative 5. So again, we can start in the rejoicing. So far it works, so far it's good. But you must check both equations, so we have to go to the second one, where we've got x plus 3y equals 1, and go ahead and plug that second one in. So x becomes negative 2 plus 3 times y, well y is 1, so 3 times 1 equals 1. That's going to be a negative 2 there. 3 times 1 is 3, so negative 2 plus 3 equals 1. Hey guys, that's actually correct as well. Negative 2 plus 3 does equal 1, and 1 equals 1. Ta-da! Happiness and joy. Ladies and gentlemen, this right here, this point is a solution. it works in one equation and the other equation. And so, yes, absolutely, happiness and joy, celebrations are in order. This is a solution, whereas 1,7 was not a solution. All right, so hopefully you at least sort of get the idea for that. Here's the thing, though. What are we going to do? We're just going to guess and check which points work and which ones don't? We could be here for years. There's got to be a better way to solve these. And quite frankly, there's several ways to solve these. We're just looking at one today. We're saying, what if we try graphing? What would that look like to have a system of equations and the one point that works in both at the same time? So I actually love graphing for this. I think the visual is fantastic. And so here's our set for the day right here. This is my graph that I'm going to use. And here's my system of equations. I wrote them side by side instead of over top of each other. I hope you're okay with that, just to give me some room to work. So I'm looking for the solution to y equals negative 2x minus 1 and x plus y equals negative 3. I want the one point that's going to work in both at the same time. And I'm going to try to find it, instead of by just guessing and checking random points, I'm going to try to find it by graphing. So, what do I know? Well, maybe I do some color coding again. Maybe I take this first one, and I do it in blue, and I say, okay, if I look at this, ooh, this is slope-intercept form. What does that mean? That means I know that my y-intercept is already given to me. That's going to be negative 1, so that's going to make graphing kind of nice. The y-intercept is here, negative 1, because we're talking mx plus b. That means the m is the negative 2. That's my slope. I love it when I see an equation in slope-intercept form, because it means that my graphing is going to be pretty quick and easy, as long as I know what I'm looking at. Yes, okay, so y-intercept, negative 1. Here's my y-axis, here's negative 1, so that means that that point is definitely on my line. And the slope of negative 2, if we think about rise over 1, that's negative 2 over 1. So essentially, because it's negative, we're going down 2 and over 1. So here's another point on my graph, down 2 and over 1. To make it interesting, I can also go up to 2 and back 1, and that would work if I think of the negative being with the 1 instead of the negative 2. But that's where my line is headed, ladies and gents, right there. That is our pattern. Our slope is negative 2. Why am I being so careful lining this up? Because quite frankly, here's the downside. All right, if we don't get the line in the exact right spot, and we're trying to solve by graphing, we won't be able to see our solution. So you have to be really, really, really accurate when you're graphing these lines. What about this one? It's not in slope-intercept form. Could I maybe put it in slope-intercept form? Yeah, why not? Let's take a look at that. If I've got x plus y equals 3, and I want to get the y by itself, so it looks kind of like that one. Excuse me. Get rid of the x. Gone. Ooh, look, there's my y by itself. 3 and x are not like terms. I can't put them together, but I can write them next to each other. That's okay. What does this mean? This means that now it looks like this guy right here. And I happen to know that because of that number on the end, the y-intercept is going to be 3. And what is my slope on this one? What number is in front of the x? Because that's not just a negative sign, right? That's a negative 1 in front of the x right there. So again, graphing works pretty well for this. My y-intercept is 3, so 1, 2, 3. So that point is there. Again, if I think of this as a fraction, we're going down 1 over 1. There's my slope. And again, very, very carefully line this up. There we go. Just like that, and just like that. Hey, are any chances that a couple of you looked at this and said, what about the cover-up method? This one would have worked really nice for the cover-up method. We can see that right here in the red. If I cover up the x, what does the y equal? 3. Boom. If I cover up the y, what does the x equal? 3. Boom. So I could have used the cover-up method there as well. You have all of these options. Pick one that you like. Okay. We're done graphing. Does that mean that we found the answer? Well, think about this visually. I love the visual on this. where do I find the one point that works in both equations? Where is the one point that's on both lines? Yes, this guy right here. That is on the blue line and the red line at the same time. 1, 2, 3, 4 to the left. 1, 2, 3, 4, 5, 6, 7 up. That means that -4, +7, that ordered pair, that right there, ladies and gents, that is my solution. That is it. Okay, so that is one way that we can approach this. We can guess and check, but that takes way too long, so graphing is a nice option. But again, what's the drawback? You have to be accurate. All right, you have to be accurate with this to make this happen. So again, like anything else, practice and see what you can do with it. All right, have fun.